In this lesson, we are going to study control flow graphs. We use CFGs to represent the control flow of a program to perform optimizations and register allocation on it. We'll first learn to identify the basic blocks of a program. Then we will create CFGs to represent how program execution moves from one block to the other. So we're going to begin this lesson with a simple quiz about what we understand as a basic block. And we're going to give you a definition and then ask you which of the following statements are true about the basic blocks. So given the definition, which is a basic block is a sequence of consecutive intermediate language statements in which the flow of control can only enter at the beginning and exit at the end. In other words, these statements execute consecutively one after the other without any control flow going out or coming in, and such sequence of statements is called as a basic block. Given this particular definition of basic block, which of the following statements must be true about such blocks? Please put a check mark against those statements which are true. The first statement is only the last statement of a basic block can be a branch statement. The second statement is any statement within a basic block can be target of a branch. And then third statement is procedure calls may occur within a basic block. So given your understanding of the basic block through this definition, which is shown here, which is a sequence of consecutive statements without any branching out or branching in of a control flow within the block, please mark the statements which you think should be true through a check mark. Please go ahead and mark your answers now. Now let's take a look at the answers to this quiz. And the first statement is in fact true. Only the last statement of a basic block can be a branch statement, because remember that the flow of control within a basic block must go from top to bottom without any transfers of control out. So therefore, there cannot be any branch sitting in the middle of a basic block. So the only place where the branch can sit is the last statement. Now the second statement, any statement within a basic block can be a target of a branch. This statement is false because obviously, again, by the definition of a basic block, the control cannot come in arbitrarily at any point during the basic block. The statements must execute one after the other, so the control can come only at the top of the basic block, and so the only target of a branch can be the first statement of a basic block. So the second statement here is false. And finally, procedure calls may occur within a basic block. This statement is true, but it is true with a caveat. Imagine a procedure call which is like a giant statement in which you have a transfer of control, but then the statement or the function call or procedure call executes and the control comes back to the point of call, origination of the call site, which is what we call as the call site of a function or a procedure call. And then it continues further down from there. If this is true, then we can simply treat the statement as though it is flowing sequentially, it is getting called, the call is executing, the control is coming back, and then the next statement starts executing. We can treat it this way, and in such a case, the procedure call can be treated as a part of a basic block. It doesn't start a new basic block. Now, this particular assumption means that the function or the procedure call is returning back necessarily always at the point of call. However, in certain languages, that is not true. For example, set jump and long jump allow in language C or C++ the transfer of control arbitrarily. The control need not come back at the point of call. So in other words, you may call a function and the function can return at a different point. And therefore, in such cases, we cannot treat that function call as a part of the basic block because it will not come back and execute the next statement. This guarantee is broken there. In such cases, we must break the basic block at that particular statement, and the control may come back, so we may rejoin back, but if it doesn't, then we'll go somewhere else. So in such cases where set jump and long jump exists, where the control is not guaranteed to return to the point of call or on the call site, we should not treat the function or the procedure call as a part of the basic block. Now, having understood what a basic block means in terms of a sequence of statements in which there is no transfer of control, they execute one after the other in that particular order from top to bottom. Given this understanding, let's apply this knowledge to a small sequence of code which is shown over here, and what we are going to ask you to do is divide this program into basic blocks by putting the block numbers in front of each one of the lines, which signify which block to which the statements belong. So the quiz is divide this program into blocks by putting B1, B2, etc. next to each line to signify which block these statements belong to, and you have been given a small code excerpt here. So please go ahead and mark your answer against the respective statements now. Now let's come back and examine the answers to this particular quiz. So if we start examining from top to bottom, we can see that the statement w equal to 0, x is equal to x plus y is equal to 0, and then finally if x greater than z, they all execute in that particular sequence. There is no transfer of control. The statements start executing at the top, and finally we hit a branch statement over here, and all of these statements therefore belong to the same basic block. Let's say we call it B1. After the branch, however, you can see that the control can go in two different directions. It necessarily does not flow to the next statement, because if the branch is false, you can see that we could go here to the else part. So in other words, this guarantee that this statement and the next statement necessarily always execute in that order is broken, and therefore we start a new basic block here for the next statement. And so the statements which are in the body of this if y is equal to x and x plus plus, they will execute together again in a linear order, but again the statement following that which is belonging to else part will not, because if then part executes, we will not actually execute else part, we will actually come here straight. And so therefore the second basic block B2, which consists of y is equal to x and x plus plus, will end here. We'll call that as B2. Continuing the same way, the branch is coming in here, because if the if predicate is false, we are going to come here and start executing, and therefore this will start a new basic block. Y equal to z will start B3, z plus plus will be a part of that as well. Again, if we examine further down, B4, which is right after this, it's possible to come to B4 from the if predicate side. For example, if the predicate is true, we are going to execute that, and then we are going to skip this particular else part and jump here, because of which again the guarantee that z plus plus and y x plus z always execute together in that particular order is also broken, because we could just come straight away here without going through z plus plus, and therefore B4 is now where the last statement belongs to, the basic block B4, and so that is the solution over here. So as you must have noticed here, whenever there is a branch, we must break off from a current basic block. Whenever there is a branch in, there is a jump inside a particular statement, we should again break off from the previous basic block. And these are the rules which we are going to use further in terms of determining the basic blocks. So having introduced the concept of basic blocks, now we are going to actually find the basic blocks from the IR code, and we are going to look at some simple rules and an algorithm which will help finding the basic blocks from IR. So the way the basic block determination works is we are going to identify each basic block by its lead statement, which is called as a leader statement, which is the first statement in that basic block. We are going to identify that, and from there we are going to pick up the corresponding basic block which belongs to that leader statement. And here are the rules for finding the leaders. One simple rule is the first statement of the function call or the procedure call is the leader, because that's where the control really enters in terms of its execution. Second rule is any statement that is the target of a branch statement is also a leader. The reason for the second rule is that it's very simple. Again, the control is going to come in at this particular statement through a branch, and so the previous statement and this will not execute necessarily in that order. Without executing the previous statement, we'll start executing the target of this branch, and that's why the target of the branch starts a new basic block, or that particular statement is a leader of that particular block. And then the third rule is this: any statement that immediately follows a branch or a return statement is a leader. Why is that the case? Again, this guarantee is broken that it will necessarily execute. And so if, for example, if you consider a statement which is coming right after the branch or a return statement, there is no guarantee it will get executed. If the branch is taken, for example, this statement will not get executed. And similarly is the case with the return. And therefore, a statement that follows the branch or return starts a new basic block or is a leader of that block. So now, having seen these rules, what we are going to do is we are going to take a small source level code. We have shown an intermediate representation that is already generated for you from this particular code. So in other words, this intermediate state representation is corresponding to this source code. And what we are asking you to do is to apply these three rules and check all the leader statements. What are these three rules? These are the three rules that we saw about determining the leader, the first statement, then the target of a branch, and then the statement that follows a branch or return. This is the three different ways to determine a leader, and the next set of statements identifies a block. So what we are asking you to do is identify, using these rules, the leaders in this segment that we are showing here. So please go ahead and apply these rules and put a check mark against all the leaders that you see in this particular IR. Please go ahead and mark your answers now. So I hope the last discussion gives you a very clear picture of how the compiler phases interact with each other, how do they cooperate, do a lot of checking, and then convert the higher level construct on a line by line or a statement by statement basis to its lower level counterpart, which is the intermediate code. So the compiler has two key parts. One is called as front end, which does the lexical analysis, which is the scanning activity, which is to scan and find out or group the characters into the words. Then syntactic analysis, which is the parsing, finding out if the syntax of the statement is correct. And finally, both of these checks are passed, do a semantic analysis to find out if the statement is semantically meaningful. The second and very, very important part of the compiler is really all about translation or conversion of these intermediate code into the machine level format or assembly. And those two phases are code generation, which is to take this intermediate format and convert it into an assembly level. And almost all modern compilers have this important phase, which is called as optimization phase. What is an optimization phase? Remember, with the softwares becoming extremely large and complex and very heavy in terms of their performance demands, we must make sure that not only we are translating this code for high programmer productivity into a lower level language, but we must also make sure that the code is quite efficient. And the compilers do a huge number of optimizations to improve the code efficiency, to improve the speed of the code, to sometimes improve the size of the data segment, and so on. In this class, we'll briefly touch upon, towards the end, one such optimization which is dealing with the registers, and another one which is dealing with the instruction selection. So now, having seen the big picture and having understood the phases of the compiler, we'll try to now get into the details. So we'll start with the scanning phase. The big job of scanner is to convert the input text into a stream of known objects called tokens or words and feed it to the parser. The main job of the parser is take these tokens, match them using the rules of the grammar, and to make sure that they are syntactically correct. So for that matter, the scanners use what are called as lexical rules of the language. So every programming language is defined by a whole bunch of rules. Open any programming language reference book, and at the end you will see the definition of the programming language's lexicon. The word lexicon means dictionary, and dictionary typically summarizes what are the different words that are present in a given language. A good dictionary is a comprehensive sort of reference on these words. So an alphabet of a language is very similar to our English alphabet. What are the legal characters from which we can build words? So in English language, we have A, B, C, D, E, F as the alphabet from which we can construct the words. Similarly, each language such as Java or Fortran or C++, we have a set of such characters which we use as a basis. So anything that we can form in that language must come out of that alphabet. Now, in addition, each programming language also has a grammar which tells us the syntax of the language. That is, how a legal sentence could be formed in that language. Remember how it is in English? We typically have rules in the language which tell us each English sentence should start with a subject, should have an object, should have a verb, and they should occur in a particular way, in a particular sequence in the sentence, and so on. So similarly, the rules, the syntactic rules, tell us how each of the kinds of sentences that we have in a language should look like. For example, an assignment statement should have a left-hand side variable name, followed by an equal to sign, followed by an expression, followed by a semicolon. So this is a simple rule which tells us how an assignment statement in a given language should look like. So now, some of these key concepts that we have seen so far, it's time to put them to test. Otherwise, you will fall asleep. I am just talking and you are listening, and that's not a good thing. So let us take this quick quiz to understand the tokens. So the quiz is to test our knowledge of tokenization or word formation. And the question is this: if we use a space to denote the end of a word, how many tokens or words are there in the following sentences in the quotes? The quotes and period are to be excluded. So this is a famous quote by famous computer scientist Eds Dijkstra. The question of whether a computer can think is no more interesting than the question of whether a submarine can swim. What an interesting quote. So exclude the quotes, exclude the period, and use this particular lexical rule that we have given you here to define a word, and count the total number of tokens or words that are present in this particular sentence over here. Please go ahead and fill in your answers here, the total number of tokens or words what we are looking at here. Please fill in your answers now. Now, having really seen the high-level picture of a compiler, having sort of done this exercise of what really is a token, counting the number of tokens, let's look at the process of generation of the tokens a little bit in details. That process is called as scanning. So what do you start off with? One or more source files which you are compiling, of the program that you are compiling. You start off with those. And then the scanner is going to read a character at a time from this particular file, and is going to take these characters and put these one by one into the token buffer. What really is a token buffer? The token buffer is a temporary sort of memory where the token is being assembled and is being identified. So now let's take our most famous and familiar Hello World program that we have seen in C and see the tokenization process. So here is the token buffer, here is the source program. And the first thing that the scanner has done is started scanning from here to this way, and the first character it encountered is M. It inserted that into the token buffer. The scanner has made a decision that looks like M starts some valid token in C. I don't know what that token is yet, and in order to do so, I'm going to start reading more characters. So it requests the next character to be read from the file, and it gets that as A. Said, okay, so far so good. These two words together are forming some legal token in C. So how does the scanner know that it is forming a legal token? Remember, the scanner has a set of rules given to it by the language designer, which are called as lexical rules, which tells the scanner how each one of the tokens is supposed to look like. And using those rules, it is checking this. Continuing the process, the scanner requests the next character I, and it says, yes, it is still a part of a legal token. And then finally it gets N, and it says, yes, it is still a part of a legal token. And lastly, it requests this opening parenthesis next. And at this particular point, it knows that there is no such token which starts with M and which is ending with this opening parenthesis, which is legal as per the C's lexical specification. So probably I have gone past the current token, and I must not include this opening parenthesis in the current token. That's what the decision it will take. At that particular point, the scanner will send these characters back and say, hey, I already found a legal token, which is MAIN. This opening parenthesis cannot be a part of it because the language lexicon says that it should not be. Opening parenthesis cannot be a part of MAIN, and therefore I'm going to use this to start the next token. But in the meantime, let me complete this token and send it to the parser. So at this particular point, it looks at the token, finds out what kind of token it is. In this particular case, it is the keyword MAIN, and it is returned to the parser. So what has happened in this particular process? Let's take a quick reflection on this. The scanner is scanning each character at a time. Whenever it scans a character, it knows it is starting a legal token or it is extending one of the legal tokens that is being formed. It doesn't know yet which token it is, but it knows it's one of the legal ones. And so it keeps extending it by reading characters one at a time. And then finally at a point, when it sees something which cannot legally extend a token, it knows that it has gone a little too far, and that character is probably meant to be in the next token, and it terminates the token, sending that character back, which is in this particular case an opening parenthesis, takes the remaining characters, and then finds out which token it is, and then returns that token. So this process is called as the longest match algorithm in terms of forming the tokens, and this is the algorithm which is used by all the scanners, trying to form the maximum or the longest token that is legally formed by concatenating these characters and saving the rest for the next tokens. Let us test our understanding of ambiguity or parsing by doing a small quiz. As you know, ambiguity is all about being able to apply two different sequences of rules or two different rules altogether for a given sentence, and both of them yielding the correct parse. So the question is, for this particular if-then-else statement that you see here, which is very familiar to you, the question is, can we apply two different kinds of rules to split up this statement? And if we can, then there will be an ambiguity. So your question here is, given if x is equal to 1, then if y equal to 2, print 1, else print 2. So this is the if-then-else statement that we want to parse. And then the question is, which grammar rule should be applied to parse it? Please put a checkbox in front of all the rules that you think could be applied to parse the sentence. The first rule is statement goes to if followed by expression, followed by then, followed by statement. And then the second rule is statement goes to if followed by expression, followed by then, followed by statement, followed by else, followed by another statement. And of course, each of these statements here can further be expanded using either one of these two rules. So what you're supposed to do is take this if-then-else statement and try doing an expansion in two different ways if you can, using these two different rules to be able to correctly parse or match this sentence. Please go ahead, try this out, come back and put a checkbox in front of which rules could be applied here, and go ahead and mark your answers now. Let's go to the solutions here and let's see which ones are syntactically or grammatically correct. A plus B. Is this grammatically correct? The answer is yes. How can we say that? A is really an identifier here. So this first A could be changed to an expression. Then this plus is a part of the right-hand side rule here, which is this plus. And then this B is another identifier which could be changed to this E. And so the whole thing here, A plus B, looks like E plus E here and is a valid expression, because an expression could look like that using this particular rule. And so A plus B is syntactically right. A plus B star C, is it syntactically and grammatically correct or not? And the answer is yes, it is syntactically correct. Let us see how. So we'll start off with the first rule here, E is E plus E. And you can see that the first E is same as this ID. So this A is same as this E, which is ID here. The plus is matched because that's supposed to follow by this plus. And then the second part should be an expression. The question is the second part, which is over here, B star C, a legal expression? Can we expand this expression using one rule to match these things? And the answer is yes. If we take this E and expand it to E star E, and further expand E to this ID, that gives us this B that can be matched. This star is same as that star. And then finally this E can be expanded to this ID, which is same as this C. And so by starting with the first rule, by expanding this E to ID, and then the second E to E star E, and then each one of these E's to these IDs, we are able to completely match this particular expression using a set of these kinds of rules, and therefore we can generate this type of an expression from these rules, or we can match it using these rules through their expansion, and therefore it is syntactically correct. What do you think about the third one? So let us see if we can generate this type of an expression by again applying these rules one after the other. Let us say we pick either one of these rules to match this A. So we could start here or here. Let's say we start here with the first rule, E going to E plus E, and then we expand this E to ID. So far so good. We'll be matching this A there. However, when we proceed further, we have to match this plus, and this plus is absent in this particular case. So the rule is expecting a plus operator. You have none here after this A, and so that's a syntax error. Now, you might say, that wasn't the only rule. How about the other one? Okay, let's try the other one. So if E, we start off by expanding in this particular way using the second one, we still expand E to ID. That is great, and we can match this A. But again, we run into the same problem, this time with the star operator that is expected here, and we have none here. So we have a syntax error. You might say, how about something else? How about this one? Well, as you can see this, the third rule simply cannot generate an A. Neither can the fourth one. The last one can just generate an A, but that's about all. It cannot generate any of the remaining things. So if we go through any of the other rules, we are not simply able to generate this sentence, and therefore it's a syntax error. So you can see that no matter how we proceed using which combination of rules or which rule and so on, this particular expression that we have here, A, B plus C, is simply not generatable from these rules, and therefore since none of the rules or combination thereof can generate it, it's a class of syntax error. Following it, the same logic further, and I'm going to kind of skip through some steps here. You can easily see that this particular last expression, A plus B plus parenthesized A followed by C, is also syntactically wrong. Why is that? Well, you can match this A plus B and so on using the first rule, and you can keep expanding this E, and you can expand this E to match parenthesized A. But following that, you will see that the moment we have an expansion of any E followed by this parenthesized E, we are expecting some kind of an operator here. Following that, we cannot simply leave that. With this fresh understanding of the grammars and so on, let's quickly review the working of the parser. So the main aim here is to check the syntax using the grammatical rules, as we have seen those, and also control the overall operation. So it is not just checking these rules. As you know, as we saw earlier, we want to see a partial sentence. The moment we see a partial sentence, we want to put it for semantic checks. If that is passed, we want to process it, generate the intermediate code, and then repeat this process all over. So the parser is the one which is in the control of all these activity, because it is the one which has the knowledge of how much partial sentence we look at each time before we undertake its checking for semantics and for its translation. And in this particular process, it is invoking its scanner, which is doing the job for it to produce a word or a token and returning it for matching it as per the grammar. So there are two different outcomes that are possible during the parsing. One is the failure or a syntax error, which is shown by expected operator, a missing parenthesis, and so on. You've seen these kinds of errors when you use compiler. So those are syntactic errors. But if no syntax error occurs, you keep getting the next token and tokens, and then at an appropriate point, you take the semantic actions. So now I'm going to introduce a mini grammar for a very small language, just to give an idea of how these processes work between parser and scanner. Here is a grammar for a micro C language, a language which is bare minimum things. All it is able to do is to declare only one function, which is main. So this is the declaration part of the function, the keyword main followed by opening parenthesis. The function could have a list of parameters, which is captured here as params. Following that, it could have a closing parenthesis, and then this is the body of the function. Each one of these, which are in the brackets here, declare those parts, how they look like using the rules for them. For example, parameters could be null. That means this function may not have any parameters at all. Or the parameters could be one or more variables. The parameters could look like a variable followed by a variable list, and that variable list could go through adding more and more variables using commas and variables and keep adding this, and finally it could terminate it here. Now the body of the function opens with a curly opening parenthesis. It has declarative statement before an assignment statement, which is very typical. When you write a program, you must have seen it. You declare variables, then you use them. So that's exactly what's going on here. And then finally, the body of the function is curly parenthesis closing it. What is a declarative statement here? Typically, a declarative statement could be a type followed by a list of variables, at least one, and semicolon. Each of the statements is terminated by semicolon here, which is again as per the C's syntax. And then an assignment statement is present, which could be a variable equal to an expression. The expression itself could look like a single variable or could be a list of variables connected together using operators. The operators could be plus or minus. And finally, this being a very small language called micro C, we have only two types, int and float. So we can declare variables of either types integers or floats, and we can combine them using this syntax to form expressions, and that forms a part of the assignment statements, as you see here. So we have only two statements, declarative and assignment. Declare the variables of types int or float, and then combine them to form expressions and form an assignment statement here. And then the rest of the things describe how the function headers look like. They could not have a single parameter, or they could have a list of parameters which are separated by commas, which is shown here. You can see that this language is almost non-functional. We don't have any IO here and so on. But that's just to illustrate how the syntax is checked. It's not really a language which could be used for any meaningful purpose because it has only one function, it has no IO, and so on. One important thing to note here is that we have not really prescribed anything about mixing or type compatibility here. Now that is not really a part of the grammar specification. It is a part of the semantic specification, whether, for example, we can mix an integer and float variables together in an expression. That is left to the semantic specification and is actually implemented as a part of the semantic check, not the syntactic check. So for example, what you could get away here in terms of doing syntactic check is combining A with B, and A could be int and B could be float, and that's perfectly legal as far as the syntax is concerned. But as far as semantics is concerned, it may not be allowed to mix an int and a float, and you would catch that kind of an error using semantic checks. You would pass the sentence of A plus B syntactically right, but you would block it as a semantically incorrect sentence later. So I hope I was able to give you clear distinction between syntax and semantics. And you may ask me, what is the big reason why we are separating it this way? The reason is semantic checks, most of them are very context sensitive, and most of the languages and parsing activity is context insensitive. And so we can use two different kinds of mechanisms for checking the syntax, which is much simpler, which is much less expensive than checking the semantics, and checking of semantics could get quite expensive because it has to factor in the context during the check. For example, whether A plus B is valid or not is not really dependent on where the expression occurs. Wherever it occurs, it is correct if it follows A plus B. Whereas A plus B, whether it is semantically legal or not, depends on multiple things. First, it depends on the declaration of A. Then it depends on declaration of B. Now, they are not to be found locally because they will be a part of the declarative statement. So in the declarative context that we are currently working in, Alright, I think now we are ready for checking the parser and scanner interactions, which we have been talking about. Here's this simple example. So we have this main program which is written there. It has only two A and B declared here as ints, and then it has only one assignment statement, A is equal to B. So as we discussed earlier, the parser demands the token from the scanner. The scanner goes to the file and starts scanning from here, gets MAIN followed by that opening parenthesis as we saw earlier, which doesn't form a part of a legal token. It discards that for now, looks at MAIN finds this to be a keyword token main and sends that to the parser. Now the parser gets this token and goes to the grammar and recognizes this as the first token that is expected to start any C program. How does it do that? For that matter, let's go back. So here was that grammar, and what happened was the main token came from the scanner. The parser started over here. So every C program should have the first token as the main token. That's what this particular rule says here. It got the main token from the scanner and it matched that main token with its expectation. And therefore, the program is starting off in the right way with the main token, it says, and is syntactically valid. If it had gotten any other token here as the first token apart from main, that would be a case of a syntax error. Once it matches the main token, it demands the next token. The scanner will go and generate this opening parenthesis as the next token as per the grammar rule, and you can go back and check the grammar again. That will be the next token that is expected as opening parenthesis that will get matched. And this particular process, parser calling scanner, scanner returning token to the parser, parser matching it, this whole loop will keep going on as long as the matching takes place. If the mismatch occurs, it will declare a syntax error. So here is an overview of how the parser works. The parser will start matching using a given rule. When the match takes place at a certain position in that rule, it will move to the next location in that rule to get the next token, and it will repeat this particular process. And during this particular process, it might need to expand a given thing using a given rule. How to decide which rule to use in this particular process is a different matter, but for now just assume that the parser has an ability to pick the right rule and expand to match the next token. If it cannot do so, it will declare again an error. So a mismatch will be an error. Inability to find the right rule for carrying an expansion to carry the parse further is also an error. And this is very rare, and of course no well-designed grammar will have this particular problem. But if it finds several rules, then the grammar could be ambiguous, something is wrong with it. Well-designed grammars are able to choose exactly one rule to expand the parse. Now, in the previous discussion I mentioned about getting the tokens, matching them, and suddenly at some point I said parser has to expand. So what is this expansion about? Let us visit this particular example here. So we have main as the first expected token, open parenthesis as the next expected token. But what next? Well, that depends on how this params is expanded. If we expand it using this rule, that will be one type of token that will be expected here. If the params were to be expanded using the third rule, there will be another set of expected tokens over here. So let us say that if we have the third token coming in as a variable, so the right expansion for the params then will be the third one. However, if the next token after opening parenthesis is straight away closing parenthesis, then the right expansion for that params will be null. So that in this particular case, it shows a program which has no parameters whatsoever, and the example that we were looking at earlier falls in this category. That's the main program, that simple main program that we looked at had no parameters, and therefore these params should go to null. Let us look at that example very quickly to verify this case. So as you can see in this particular simple program, we have main, opening parenthesis, and no parameters whatsoever. The parameter list is empty, and then we have a closing parenthesis. And so in this particular case, the params should go to null. This params going to null allows the next token to be matched as close parenthesis, which is what is there, which will be returned by the scanner. So what is going on here is the grammar is expressing most general ways different C programs can be generated. A particular C program that we have at hand could fit one such expansion. The one we currently are talking about has no parameters, and therefore these params will go to null and will be matched by this grammar. On the other hand, if there were other programs there which had some parameters, which had maybe one parameter or two or three or many, the params will be expanded by the compiler or the parser to generate this list of vars separated by commas to match them all, and therefore that program will be syntactically parsed appropriately. So the key decision parser has to make is for the current program, which is the right way to go. Is it this way or is it that way, to be able to match it? If the params is unable to expand using either this rule or that rule, we know that the program is syntactically incorrect and an error will be flagged appropriately as a syntactic error for the programmer to correct the program. So students, in the last slide, we saw how the parser works. The parsing algorithm has to choose a rule, a unique rule at each step to predict the next set of tokens that could be matched for the current input program. And we saw that in case we are faced with a problem of having to choose between two possible rules, then we are in trouble. So that's ambiguity. And let's try to understand the ambiguity here a little bit more clearly and its implications. So what is really an ambiguity in the grammar? So it is a property of the grammar. Sometimes the languages themselves are ambiguous, so there is no way to write a grammar which is unambiguous. But most of the times, the languages are well designed, especially the programming languages are well designed. And so some grammars could be ambiguous, which correspond to that language, and some need not be. So the language designers and the grammar designers take care in removing ambiguity so that at each step in parsing, we have a unique possibility of a rule to be chosen. So ambiguity goes to the heart of the concept of parsing. And the parsing is not just about matching tokens, but it is about putting a structure on a sentence. When we choose a rule, we are trying to understand the sentence. We are trying to find out subdivision of the sentence, and that particular rule corresponds to that subdivision. So here is an example in which the same expression could be split up in two different ways and the results could be totally different. And if we have two different rules which can be used to split up the expression, then we are going to have trouble in the semantic understanding of this particular expression. So let us take a look at this expression 2 star 2 plus 3. What we could do is we can split it up in a way that first 2 is multiplied by this 2 and then the result is added to 3, and that leads to the total result of, or the final result of 7. However, if we split it up in a different way, if we group this 2 plus 3 as a sub-expression first and then decide to multiply that sub-expression to 2, then we will get a result of 2 plus 3 is equal to 5, 5 times 2 is equal to 10, and the final answer here will be 10. So these are the two ways of splitting this expression, and they correspond to two different ways of applying the rules. First, we may apply a rule at the top level, e going to e plus e, and then we can take the leftmost e and further expand it to e star e, and if we do that, then we get the first split of the sentence. On the other hand, we could start off by applying the star before the plus. So the first expansion of e could be e goes to e star e, and then the right side e could be expanded to e plus e. And if we do it that way, then we are trying to interpret the sentence as first doing the addition followed by the multiplication, and that yields another answer. Let us test our understanding of ambiguity or parsing by doing a small quiz. As you know, ambiguity is all about being able to apply two different sequences of rules or two different rules altogether for a given sentence, and both of them yielding the correct parse. So the question is, for this particular if-then-else statement that you see here, which is very familiar to you, the question is, can we apply two different kinds of rules to split up this statement? And if we can, then there will be an ambiguity. So your question here is, given if x is equal to 1, then if y equal to 2, print 1, else print 2. So this is the if-then-else statement that we want to parse. And then the question is, which grammar rule should be applied to parse it? Please put a checkbox in front of all the rules that you think could be applied to parse the sentence. The first rule is statement goes to if followed by expression followed by then followed by statement. And then the second rule is statement goes to if followed by expression followed by then followed by statement followed by else followed by another statement. And of course, each of these statements here can further be expanded using either one of these two rules. So what you're supposed to do is take this if-then-else statement and try doing an expansion in two different ways if you can, using these two different rules to be able to correctly parse or match this sentence. Please go ahead, try this out, come back and put a checkbox in front of which rules could be applied here, and go ahead and mark your answers now. Now let's take a look at the answers. So please focus on the sentence here which is shown in the box. What we are trying to do here is we are trying to apply a rule to match this sentence. And as you can clearly see it here, we could take this statement here and expand it using this particular rule, the second rule, and that will match this sentence perfectly. And if we do that, then this becomes a statement, and then we can apply the first rule to that statement going, for example, over here to if equal to then statement. So in other words, this particular sentence could be treated as one sentence, and we could use this rule, second rule, to match it completely. That is one way of doing things, and that's why this is possible to apply. And what we do in this particular case is group this else or associate this else with this if, and therefore we get this type of a sentence. But that's not the only way to parse it. What we could do is we could associate this else with the top level if, and then the middle sentence here without this else could be broken up using this particular first rule. The second possibility is, instead of taking this whole sentence as one, we just take the part without the else, we apply the rule, and that could be matched by using this particular rule, the first rule. So we could do this matching, and this will become a statement here, and then the complete sentence could be matched, of course, by using this particular rule. So in other words, this is also a legitimate way of breaking the sentence. And so we see that for this particular statement, we have two different rules in which we can go about. We can start off at the topmost level by applying this rule and matching this expression here, then over here. This whole thing becomes a statement here, and then else, and this print becomes statement here. And then for this statement, we go ahead and apply this rule to match it. That's one way of doing it. So start with second, expand the statement after then by using this rule which matches this. So that's one way of doing it. Second way of doing it is to associate this else with this if, as shown here. And how do we do this? In this particular case, we don't start with the second rule, we start with the first rule. So we say if expression, then statement. Then we take this whole statement and expand it using the second rule and match it by using its right-hand side like this. Now, these form two different sequences, of course. First rule followed by second rule is one way, and the second way is second rule followed by the first rule. The biggest difference there is where do we associate this else? If we do it this way, this else is associated with the inner if, and that means when y is not equal to 2, we are going to execute this one. However, if we associate this else with the outer if, then this print2 is going to execute, and we are going to see a number 2 on the screen when x is not equal to 1. So there are totally different meanings attached to these sentences, and therefore, because of two different sequences which are possible, we are creating an ambiguity here, which is not a good thing, and we must remove it. This problem is very typical about association of a particular operator at the innermost level or outermost level, and it's exactly the same problem that we faced in earlier cases as well. So in this particular case, there was no precedence in terms of which rule should be applied first, and therefore again, there was no precedence given to star over plus. The correct meaning of this sentence, as we understand it, is to do the PEMDAS, or to do the multiplication before the addition, parenthesis, exponentiation, multiplication, and so on, as we know in the PEMDAS. And so to do a multiplication before we do an addition, that is the right interpretation. And so this particular other implementation should not be allowed. So the grammar should be written that we are not able to apply the rules in two different sequences, nor we are able to pick two different potential rules at a given point in the parse. When that is the case, the grammar is unambiguous. Again, the programming languages are designed to be unambiguous, so some grammars corresponding to them may be ambiguous. So now, having understood the overall working of parsing, the concepts of ambiguity, the way to change a grammar to make it unambiguous and so on, we're going to complete the loop between scanning and parsing to really understand this process very clearly, and we'll do so through the simple example program here, which is written in micro C, and we'll see the parser scanner interactions. We'll see how the grammar is being expanded, the rules are being chosen, and so on to match the tokens generated. So here we go. The compiler kicks in, the parser asks for a token from the scanner, and here is the grammar that is showing the expected set of tokens at the parser end. And so the first token that is expected, as you can see, this is the starting point of parsing. Every C program that is called as the start symbol of the grammar, it expands from there using its rule. So it starts and picks this rule for a start symbol, and it expands it and says, hey, the first token that I'm expecting here is main. Give me the token. So the scanner goes, generates the token main as seen here, and sends it to the parser. The parser matches this token with its expectation and checks both of them off, saying that you're good because that's what I was expecting, and syntactically you are just fine. After that, the parser proceeds ahead to the remainder of this rule, and here is another token that it is seeing, which is it's expecting open parenthesis, goes to the scanner goes further, generates this token. As you can see, it is going to be an open parenthesis, and it matches the expected token. Both are checked off by the parser, saying that syntactically you are just fine again, and parser proceeds further. Now the parser is at this particular place, params, and it faces a choice of a rule for expanding the params. One choice is to go to null. Second is to expand it to a list of parameters, which is a list of variables. If you look at the grammar, there are two choices for params here. One is a variable could be expected here, or params should be let go to null, and the parser gets a token closing parenthesis. Now if you look at this very carefully, the only way this closing parenthesis can be matched by the parser is by letting params go to null. So the parser intelligently makes this choice, says that there are two types of C programs that could exist here, one with parameters, another one without parameters. Looks to me that this is a program that I'm parsing without any parameters, because it is directly sending me this particular token, which is after these parameters, and so I must nullify these parameters. So it chooses a rule which nullifies this using params going to null, and then goes ahead and matches this particular token to the expected one after params. You can see that the parser is extremely intelligent here. What it is keeping track of is two different possibilities. One possibility is var. So if it would have gotten a var, params would have been expanded using the rule which expands to var on the right hand side. On the other hand, if it gets something which is coming after params, that means params should simply go to null. It will let it go to null, choose that rule, and then the token will be matched to what is expected after this. So the parser is maintaining some kind of an expectation, or expectations rather, and depending on which one is being met, it is choosing the rule correspondingly. This way of doing parsing is also called as predictive parsing. It is trying to predict which rule to be used for nullifying it. The other set of parsers, what they do is they could choose a given rule. When they say things cannot be matched by using that rule, they will backtrack. They will try another alternative. So in this case, param could have been first expanded to var, and seeing that var and close parent cannot match, it would have backtracked and then it would have chosen another rule for params. That would have nullified params and matched close parenthesis with what is expected here, and that parse would have been successful, and then it will proceed further. But for all practical parsers, they are predictive. They are already able to eliminate other rules which will not work and choose the exact right one when nullified will lead to this particular match. How they do that? Well, that's a part of the later discussion in the class. Right now we are just trying to understand how the parsers work rather than how do they choose the rules. So now we are at a point when everything until close parenthesis is matched. Now we are faced with an expansion of main body, and the incoming token is curly open. There's only one rule for main body which starts with curly open, and we expand that, and that's the token which is expected. That's the incoming token. Again we match it. We are done. We are syntactically correct. Next, we get that incoming token as int, and we are faced with an expansion of declarative statement. Declarative statement is then expanded using its rule. Again, there's only one rule here. But for type, there are two rules. One is int and the second is float. And again, the parser will make a choice of expanding. So far, we have seen in details the process of parsing in terms of different rules, the concept of ambiguities, and how to make sure there is no ambiguity in the grammar and so on. And that's all about syntax. We also know that many times we get semantic errors, and we have talked a little bit about those in terms of type mismatches and so on, undeclared variables and so on. So now let's test our knowledge through a simple quiz to clearly distinguish between syntax and semantics. And we are going to base this on your knowledge of C programming language, which we are sure that you guys are masters of. And what we are asking here is, assuming we are using C programming language, determine which statements are syntactically incorrect, which are semantically incorrect, and which are both syntactically and semantically incorrect. So put A where you think statements are syntactically incorrect only, put B where they are semantically incorrect only, and put C where you think they are both syntactically and semantically incorrect in the following program segment. I'm going to read this program. So we have int main opening parenthesis, closing parenthesis, opening curly parenthesis. The first is a declarative statement, int a comma b comma c, semicolon. The first statement in the body of the program is a plus minus equal to b. The second statement is a is equal to b plus c. The third statement is d is equal to a plus b plus semicolon. And then the fourth statement is d is equal to a plus b semicolon. What you are supposed to do here is on the right hand side boxes next to each one of them, put a, b, c or none of them if you think they're syntactically and semantically correct. Please go ahead and write your responses now in these boxes which are shown. Let's now go over the solution to the quiz and let's analyze those. So what you first see here is everything is correct here syntactically. It's a program which is written on the first line, int main, opening closing parenthesis, int a comma b comma c, semicolon. Everything is fine up to this particular point in terms of the syntax and so on. And we are having a declaration here of a, b, and c. Let's go to the first statement here, a plus minus equal to b. What do you think? Is it syntactically wrong, semantically wrong, or both syntactically and semantically wrong? Then the answer to that is, it is syntactically wrong because there is no such operator here called plus minus. When the statement has a syntax error, typically the operator is undefined to begin with, and so there is no reason for checking it for semantics. But syntactically, we know that there is an operator called either plus or minus equal to b, which is a is equal to a plus b or a is equal to a minus b, but there is no such operator as plus minus on the left hand side of equal to, and so this is syntactically wrong. So there is no such operator in C. Now the second one, a is equal to b plus c. What do you think? Statement 2 is syntactically and semantically correct. The reason is, obviously this is an assignment statement in C. There's a plus operator in between and equal to and semicolon at the end, so it's syntactically right. Now what about its semantics? The first question that we ask ourselves is, are A, B, and C declared and are available in this current scope? They're all declared and are all available. So that part is fine. The second question that we ask is, are B and C compatible under plus operator? They are, because they are ints. And finally, is the result compatible with the left-hand side in terms of its type? That is also true, and therefore this is semantically fine. Let's go to the third one. The third one has in fact two types of problems. If you see the sentence a plus b plus, after that is nothing. So that's a syntactic issue because there is something missing here in the expression. There should be a c or some such thing which is missing after this plus operator, so that's a syntax error. And in addition, there is also a semantic error because we also have a d involved in this sentence, and d is not really declared here, is not available. We don't know what d is, and so we cannot do a type checking. We do not think that d is even available to be used here without declaring it first. So that's a semantic error. Syntactically, this D is just fine because this is a var equal to expression. Of course, the expression has an issue, but assuming that that problem is a different one, var is equal to expression, that as far as this is concerned, this is a var. So syntactically it is just fine. Semantically it is not, because D is not declared. So here is a summary of what I just said. So there is a missing operand after second plus operator and undeclared D, and that causes a semantic error. Remember, whether D is declared or not is checked by the semantic phase, and that's why this is a semantic error. Finally, let's go to the last one. What do you think about this statement? As far as syntax is concerned, it is just fine. Var is equal to expression, and the expression is perfect in this case, A plus B. However, D is undeclared, and so this is purely a semantic error, which is shown here as B. So this quiz should give you a very clear separation of ideas between syntax and semantics. Semantics has to do with declaration of variables, the type compatibility, and so on. And it's a much more expensive operation to check because it uses the context, whether something is declared here, and we have to note this information in the symbol table, and then we are going to use this for checking whether these operations are type matched and whether they are meaningful because of the declared values or undeclared values make them semantically meaningless. On the other hand, syntax checking is a very local activity. It is confined to just within a statement, and we need no knowledge of what happened before to decide the syntax errors here. We know that this operand is simply missing. Based on the grammar, we know that an expression should have another operand here, and when that is missing, that gives us a syntax error. So syntax error checking is much more faster. That is why in compilers, we do phase ordering wise syntax checking before we do semantics. So if we find a program to be syntactically problematic, then there is no need for checking it further for semantics. And so this is a good example of the third statement, which is over here. So the last discussion shows you that the key part of semantic checking is to be able to hold the values in symbol tables and then use some checks to find out whether they are declared and to find out their types and to do the type matching and so on. So let's take a look at some of these semantic checking in a little bit of details, which will complete our discussion of the front end of the compiler. This is our last phase in the front end. We have done scanning, we have done parsing, and then we are on to semantic checks now to understand them in somewhat of a detail. So the key structure that I have been talking about so far is symbol table. And what is symbol table? The symbol table is showing us what are the different values which are declared in the program and which are available within the current scope. For example, if we encounter a declarative statement int a comma b, that declares a and b to be of type integer, and they are available from this point onwards in the current and inner scopes. Almost all the languages are block structured. That means whatever values are declared in a current scope are also available in the inner scope. Unless they are redeclared, they remain visible in the inner scope. And so the way the compiler treats this is whenever it processes a declaration statement through the grammar, it goes ahead, picks up all the values which are present in the declarative statement, and it stores it internally in a table called symbol table. How does it look like? It has names which are declared. It has their underlying types which are attached to them. And it also declares the scope in which they are visible. So in this particular case, we'll assume that these are declared within main, as we have seen these examples. And so within that scope, we can operate on them, we can add them up, we can read a value into them, we can print their values and so on. So those remain visible in the scope, which is what a basic symbol table shows. Now you might ask me, why is this stored in this particular way? Remember, what we are trying to do here is take these values, hold their attributes in a table, and later on when we encounter their use in the body of main's function, we'll have to keep checking them if they are declared, if they have compatibility under types and so on. And so for that reason, we need to save this information in a table and later use it for looking up the values if they are declared, and if they are declared to find their types, to do the type checking and those kinds of things. So now let's look at the symbol tables and the semantic actions which are pertinent to them. So first important action is enter variable declarations into the symbol table. That is one of the biggest semantic actions that need to be taken care on the declarative statements. The second important action is during the processing of the body of the functions and so on, we look up this information in the symbol table, especially if the variables are declared or not. And if they are declared, we take their information about their types and so on from the symbol table to do the type checking. So before we undertake the type checking, we do what is called as the binding analysis. So let's say we are looking up a particular name A. Now there are several possibilities. There could be an A present in the innermost scope. There could be another A declared in the outer scope. There could be A sent as a parameter and so on. So by looking at the scoping rules, which the block structure has a certain kind of scoping rule that it exposes the innermost declared A, we will bind this A to the innermost declaration. And if we don't find it in there, then we keep going up in terms of scopes and find that A which is in the scope which is exposed to the current scope where A is declared. So this type of analysis is called as binding analysis, and it uses scoping rules of the block structure and so on. Once we determine which A it is amongst the multiple possibilities, we know what type it carries based on that declaration. And we bring that particular type in for doing the type compatibility check. Once we do the type checking, we know that we are generating a sub-expression. Now the sub-expression is going to have its own type, and that type will be used for doing further checking in which the sub-expression itself participates. This particular activity is called keeping the semantic context of the processing. Let's look at this last concept, which might be a little bit ambiguous, through an example. So let us see what is going on here. We are trying to add A plus B plus C here. The first thing that we are going to do is do the binding on A, determine A's type, do the binding on B, determine B's type, and do the type compatibility check as shown here. And then we have ready to process the expression A plus B. Now, since in this particular case, let's assume for a minute that they were both integers, the type of the result is also an integer, and that is going to be generated here by carrying out this A plus B resulting in a value T1, and the T1's type is going to be integer. Then we proceed next, we do the binding analysis on this C, we determine its type, that happens to be integer, let's say, and then we have the type of this sub-expression's result in T1, which is integer. This is also integer. We do the type compatibility check here, which is passed, and then the type of the resulting is T2. So what is going on here, as you can see here, we are trying to keep the semantic context. How are we doing this? We are generating a sub-expression and its result, and the result of the sub-expression is stored in this particular T1, which we call as temporary, which is maintaining this context, and the type that is assigned to this is the same as that of the sub-expression. Remember, these are declared values, but this is a synthesized value to hold temporarily the value of the sub-expression. And that is where we are proclaiming that the type of the sub-expression A plus B is being maintained as int here and is being carried further to do a further type checking with regard to C, which is coming here. And similarly, we'll propagate the type to T2. If the sub-expression were to be extended further, we'll carry out the context propagation by using T2 further, just like we did it for T1. This whole thing will keep going on, and that's one of the important activities in semantic analysis, to keep track of the types of sub-expressions that are generated and to make sure they are compatible. Now, having understood the general working of semantic analysis, let us look at how one could implement semantic analysis in a simple way. So we are going to illustrate it briefly now, and then we'll come back in many more details later in the class. So what is going on is a simple way of implementing this is to embed what are called as action symbols in the grammar. What is really an action symbol? An action symbol is simply telling us about a semantic function or a procedure which is being triggered at that particular point during parsing when we have seen a sub-sentence here which is processed. And what are these procedures doing? They are doing some semantic analysis. They are getting some information from symbol table. They are installing some information in symbol table and things like that. They are doing type checking and those kinds of things. And when the semantic checks are passed, they return true, and the control goes back to the parser, and the parser says, hey, the semantic checks are correct now. I'm going to start doing some code generation. So that is where these interactions take place. So in short, semantic procedures are called by the parser at appropriate places during parsing when enough of a sentential form is seen. Enough of a sentence is seen For example, we are parsing an expression and we have seen the one first operand, second operand, and an operator. And of course, the expression is much bigger than that because there are 5 or 7 or 10 maybe operands as far as this expression is concerned. But just seeing 2 operands and their operator is enough for processing this sub-expression, and that is where the first semantic action will be called to do the type checking on them. This is an example. After we seeing A plus B, although we have not seen C yet, we are ready to do some semantic processing, and that's what we did in the last slide. We first did a lookup on A, did a lookup on B, found their binding analysis, then we did a type compatibility check, and when everything was passed, we generated a sub-expression and passed on its context to the temporary value which is carrying the result of this. And that's how the semantic analysis then returned over here. And then we did something further by again triggering it after by saying C, again doing the analysis on these sub-expression and so on. Therefore, you can see that an action symbol in the grammar will be triggered after seeing the first 2 operands without waiting for seeing the complete sub-expression. Typically, this activity of semantic analysis will be implemented by using a semantic stack, and what it will do is it will store the semantic context, it will propagate it, and procedures and functions will be called to operate on the stack, and they will manipulate the values and return the values, push the new records which carry the semantic context, and so on. So now we are going to give you a little bit of an idea of the semantic actions and the action symbols which are embedded in the grammar and how they are called. Let's take a simple look at this particular declarative statement. What we have here is type followed by var list and so on. And then the type expands to int or float. Var list expands to a list of variables starting with each var. It can stop only at var or it can keep expanding. So that's the basic grammar as we have seen earlier. And the vars expand to the identifiers. And what we have here is different semantic actions which are being called. So let us say we start with this particular float a, b, c. What's going to happen is we are going to start expanding this into type. The type is going to expand into the float. That float is going to match with this. And then we are going to trigger a semantic analysis which is called as put type. What is put type doing? Put type is simply creating a record on the semantic stack of the given type. What is the given type here? Float. So what is its purpose? The purpose is somehow to attach this type to the list of these variables. So what we are trying to do on the semantic stack is to create this record, then put the records for each of these variables on top of it, and then link them together, process this as one unit, and then finally put it in the symbol table. So that's the whole action we are implementing here through multiple semantic symbols which are getting triggered. So let's come back to this. So what's going on first is put type is going to take float, create this semantics record of the type record on the semantic stack, which will be at the bottom of the stack. Next, the parsing will continue to var list. The var list will first get expanded. In this case, using multiple invocations, it will go here because there are multiple variables. First, this var will get expanded. Now the process declaration will be called. What is the job of process declaration? Process declaration builds declarative record for the variable on the stack. As I was mentioning, first we have built a type record. On top of that, we are now building declarative records for all the variables which are a part of the declarative statement. So A's record will be built here. The parser will proceed further in this case. It will expand this var list again to go to var. This var will again get matched second time. That will be B. We'll call this process declaration again. Now this time we'll be building the semantic record for B on the top of the stack. Now this var will get expanded to ID, and this time the ID will be corresponding to this C. So finally we'll be building the record for C on the top of the stack. We're done at this particular point building all the records for all the variables. So as you can see, the last one expansion took place over here. So next we'll be calling add declaration. What is add declaration going to do? It is going to build what is called as a declarative chain. What is a declarative chain? So far we have simply put all these records on the stack, but we are going to link them together saying that all these variables are of this particular type. This is how it is going to look. Initially we had built the stack using the type record. Then there is a record for the first variable A. This is a record for the second variable B, third variable C. And then we have built a declarative chain by linking all these together, saying that all these three are belonging to this particular type. So that's the function call that took place over here, add declaration. And finally, this var list is complete now because all was matched by using the parsers. And then we are going to go here, and then finally we are going to match this semicolon, and at the end we are going to call do declaration. Now what is do declaration doing here? Do declaration's job is to take this semantic stack, whatever was built into the semantic stack using the semantic context, traverse the chain on the stack by using pointers, and then take each one of these semantic records and push those into the symbol table. Remember, we're using the semantic stack during the building process. Our goal is to pick up all this information, put it in the symbol table, and at this particular point, we'll get rid of all the stuff from the stack. So at this particular point, do declaration, when it is called over here, we are going to take all of these, traverse the semantic stack from top to bottom using the pointers. This is what the do declaration is going to do. Pick up all this information, and corresponding to each one of them, we are going to put them in the symbol table. Their type information, which is here, which is float, is being noted here. Remember, it is just given in some integer for some base type here. And the current scope of declaration, that is also tracked by the semantic analysis. We assume that, let's say, this is in the third level of nesting of the scope, and that is also noted over here. So at this particular point, we took the information which is on the semantic stack, which we created using semantic analysis by putting the semantic context. What is the semantic context here again? The semantic context here is for this particular type, this is the list of variables which get this type. So we created this context, we attached this context to all these variables. We took this, we built this information first in the semantic stack. Then we took it and then we put it in the symbol table. So at this point, we are done with this particular information. So the last thing the do declaration is going to do is get rid of all of these from the semantic stack, free it up. We're done with this particular processing of the declarative statement. Now, whatever information we need, it's there. We have stored it. So we are ready to use it to find out the type compatibility, to do the binding analysis, and so on that we need to do. So please go through this very carefully. Again, what is being done here is in the grammar, we have embedded these symbols. What really happens is the way the parser works is it expands it, keeps expanding it. Whenever the expansions are complete, let's say by float, put type is called, which is an action symbol which is following that. And this is nothing but a function. The function's description, what it will do is there given here. So it will take this information which is coming back from this float, and then it will create a type record over here, and it will create the right semantic context. Furthermore, again, same process repeats. The parser decides which rules to use, of course, depending on whatever previous discussion that we have seen. That's completely independent of this. And depending on the rules that it uses, it will do the matching. Once the match takes place, it will trigger the next action for the semantics, which is process declaration. It will take the current identifier, put it on the stack, and so on. And it will, in this process, build a chain of declarative context, attaching it to the type. As shown over here, it has created this context and attached these three things to this. Then finally, once the complete sentence is processed, it will transfer the information from the semantic stack onto the symbol table, as shown here. And at that particular point, it will abolish the semantic stack. So let us take a look at semantic actions. Now, what we showed you earlier is only one kind of an action, how to process a declarative statement. But that's not the only one. In fact, there are many different kinds of semantic actions. They're embedded in different parts of the grammar, and they do many different things. Apart from processing declarative statements, the other important activities involve doing the binding analysis, as we showed, finding out which A we are talking about here, then doing type compatibility check, scoping availability of values, etc. And then once the scope is closed, we are going to get rid of all the values which are declared in that scope from the symbol table. That's an important activity. And then while processing the body of the functions, we are going to do type compatibility. We are going to generate temporaries as we showed them earlier. T1 was a temporary. T1 is equal to A plus B. So when we process a sub-expression, we evaluated and gave it a name as T1. We attached type to it, kept the semantic context. We propagated them to do the further processing. This is what we are talking about here. We created this temporary, we generated this type of a code, and we propagated the attributes of type to this It's also current scope will be assigned same as whatever we are processing in. And so this is the context or bookkeeping that is being done by the semantic procedures. That's another important activity. So this is a summary of checking versus translation. There are two different classifications of semantic actions, and this is a summary of those. So far we have discussed in details or in somewhat of a detail 3 important phases of the front end of the compiler. But now let's take a look at the full compiler structure, and here is how it looks. So these are the 3 phases that we saw: scanner, parser, and semantic analysis operating in tandem with each other. Once the semantic checks are passed, we lower the current code that we are looking at into an intermediate representation. So this is one important form of intermediate representation. This is how the intermediate representation of this expression will look like. You can see that it is close to the assembly because it has 2 operands and the result with the operator, and the result is typically a temporary. Now remember that this is not really an assembly because many times we'll have to load the values of A and B from the main memory. So that will be additional instructions there. Secondly, we have not done any register assignment here, nor have we selected any particular instruction. We are just looking at an abstract operation of addition. But we have, instead of saying that we are just adding A, B, C together, we have broken it down 2 things at a time, and the result is stored in a temporary value. So that's why this is called as the intermediate representation. There are 4 fields to these, and this is one important form of representation which is called as quad structure. Quad means 4, and it has 4 fields. That's why it is called as a quad structure. Once the intermediate code is really generated by doing these 3 different kind of analyses, then the second phase of the compiler, which is called as backend, kicks in. The first thing it does is analyzes and optimizes the intermediate representation, does register allocation, then instruction selection, then instruction scheduling, and finally what we get is an assembly code, which is the output of the compiler.